Yes. Francois, well, Ferdinand, it could be also Ferdinand.
No, it's Francois.
Germinet, and he will speak about localization and delocalization in the quantum world system.
Yeah, thank you very much.
No.
I would like to thank the organizers for giving me the opportunity to give this talk, and especially actually the last talk of this very nice semester. So in advance, I would like to really thank all the organizers for these beautiful meetings with an S at meetings, and for this full semester. It was a very good idea. I enjoyed my stay last August, and I enjoyed my stay right now here. So the talk I will give you will be a mix of a review talk and some recent extensions that we did. The main results are results obtained with Abel Klein and Jeff Schenker. But meanwhile, I will recall you some other results from different papers. So I work in L2 of RD, of R2, so the two-dimensional system, and I consider random perturbations, Anderson type perturbations of the Landau Hamiltonian. Okay, so just to fix notations, I will denote by H naught the Landau Hamiltonian. So this with A naught is going to be equal to B half minus Y minus X2 X1. Okay, so B is the strength of the magnetic field, and the random potential just to make it simple, I will assume that here, and then I will consider extensions. But first, I will assume that it is a collection of bumps with some random amplitudes. So pretty much what you have seen many times in previous talks. And omega I, so first the U will be positive here. U will be positive, L infinity, and strictly positive. Positive. It's like this. I mean, I will just draw a picture. U has this shape, right? And as for the omega I, compact support, yes. And as for the omega I, there are IID random variables with a distribution d mu of omega naught, which is equals to rho omega naught d omega naught. And I will assume here that it has a zero mean. Okay. So rho is an even function. Okay, and of course it has a bounded density. Okay. Yeah. Okay, so this will be the main model for which I will give you some results. I mean, I will spend time on it, and also I will be interested in several extensions of this. Which I think are of interest. So first, some V omega which are just ergodic and not only of this special form. So for instance, including quasi-periodic models, potential. So this is one possible extension. Then models for which here you see well, okay, no, you don't see because I did not write it. Rho has a compact support also. So the distribution is also like this. And I will be interested in V omega with Gaussian type random variables, so distribution rho. So in this case, the spectrum is actually the full real line, and it is quite interesting to look at this type of model, and also some V omega which are non-ergodic. Namely, for instance, if you replace Z2, the underlying lattice Z2, by some set which is not regular but quite homogeneous in the space, so let's say a Delaunay set, then can you say some things? Can you say things about these models? Okay, let me remind you that at least if V omega is ergodic, so this is this case, and what I wrote before, then you have some covariance property. You have seen this many times before, I guess. So you have the magnetic translations, UA, H omega. Let me say that H omega is H naught plus V omega, and I will add a coupling constant lambda in front of it. So if you conjugate your Hamiltonian with respect to the magnetic translations, then you get H tau A omega, where tau A is a translation in the omega space. And this implies, for instance, that the spectrum is almost surely the same. Of course, in the non-ergodic case, you don't have this anymore. Ilya, question?
Oh, I got a question.
Okay, so what is the picture? So I will draw some pictures of the spectrum, just to start with something, and then I will describe the results. So if you start with zero disorder, zero potential, then what you have is just, of course, the Landau levels. So that's going to be B, 3B, 5B, etc. And since I took an even, random variable with zero mean, as you increase the disorder, the spectrum will actually spread into these so-called Landau gaps, and you have a picture like this. And for instance, if you consider a lambda here, then the spectrum, you can show that the spectrum is located in some compact region here, and actually in some under some hypotheses, in particular in this case, you can show that the spectrum is actually the full interval, almost surely. Okay.
What is the vertical axis?
Yeah.
Lambda.
It's lambda. And here is the spectrum. Okay? So at lambda equals to 0, the spectrum is just the spectrum of the Landau Hamiltonian, and then the Landau band, the Landau levels, they split as you add the random potential, and you get a band like this. Okay? And the result will be the following one. Near the edges here, you have localization, and And in this region, in the blue region, you have an energy of delocalization.
So you don't want to say they're all delocalized there, do you?
No, no.
There is.
I will say there exists an energy. I will actually maybe say something more.
One
conjecture.
energy.
Yeah, you will see the result. Okay, okay. You will see the result. And there is another situation that I am interested in. That's actually the second point here when V omega is unbounded from below. Then the picture is like this. For lambda equals to 0, you just have these points. And as soon as lambda is strictly positive, the spectrum is everywhere. Okay. The spectrum will be the full line. And it becomes, you will see that you can get results here in a quite straightforward way. But you need more materials to deal with this very particular model. Okay. So, and the problem here, the difference between here and here is that you can reach some region of delocalization by passing through gaps, while here you cannot. You just jump from one situation, a very particular situation, to another situation where you just have localization everywhere. So in particular, you will need some continuity of the density of states and of the whole conductance and a bit more of this to handle this situation. Okay, and so again, the result will be that inside the Landau bands, you have localization, and there exists an energy somewhere here where you have some delocalization.
Is it a region or is it a single point?
A single point. Well, actually, I will comment on that. Okay, I will say something more about this. Yeah.
I imagine you want to say it's a single point at least.
Yeah, it's a single point at least.
Well, so at least is at least a rigorous statement.
Yeah.
And
I will state the theorem.
What is known phenomenologically from numerics and so on, and what is rigorous.
Let me go forward, and you will see the statement, and I will comment on that. Right? Okay. So now I would like to remind you the different pictures that we have of localization. So one focus on localization. So what I mean about that is what is the type of result that we can prove inside this region where I claim that we have localization. Well, the first notion of localization is, of course, Anderson localization. That means pure point spectrum plus exponentially decaying eigenfunctions. In particular, if you have phi for almost every omega, if you have psi omega n an eigenfunction, and you look at what this is a unit cube, this is a characteristic function of a unit cube at site x. If you look at the size of this eigenfunction near x, what you get is a constant that depends on omega and n, and then exponential some mass x. Or if you want, you can always add, this is for free and you don't need it here, but you can always assume that you have one point where it is maximum and it decays exponentially fast from outside, from this point. And you have a constant, and one problem will be how to control this constant.
Question. If I look at your left model, and if I go very far in lambda,
so if I go,
then these triangles overlap.
yes, yes,
Do you have any statement for that?
yes. And also, this is also something that happens here, because here, as soon as lambda is strictly positive, all the bands are mixed. All right? Okay. But what happens here, if you go to very, very high lambda, you see, you can treat the case where this touch like this, and then a little bit further. But an important question is, and I don't know the answer, is what happens if lambda gets much, much bigger. In particular, you expect that because of very strong interactions of the bands, you will witness some deviation of these things here. And for instance, get the nullity of the whole conductance in a region around here. But this is far from, okay, there is no result whatsoever on this. There was a result of Belissard and Nakamura, and we did also something with Jean-Michel on this, but it is a different regime. It is a different regime. It is not exactly this. It is not as fair as this model. Let's say. Let me put it this way. Okay. So let me proceed. So this is Anderson localization, and it has been pointed out already, in particular in Jonathan Breuer's talk yesterday, that this is not enough to get some localization of wave packets. In particular, you can have delocalization and transport even with Anderson localization or pure point spectrum with decaying eigenfunctions. And maybe the most celebrated model for this is the rank 1 perturbation of the almost Mathieu model done by Del Rio, Jitomiskaya, Lass and Simon. But since that, there are many, many other examples for random decaying potentials in 1D, sparse potentials, and also a so-called dimer model, which is a discrete model, a discrete Anderson model, where with Bernoulli random variables, where instead of having IID random variables, you couple them by pairs, and you get some energies. You have pure point spectrum with exponentially localized eigenfunctions and fast transport at some very particular energies, and it is a nice result of Jitomirskaya, Stolz, and Schuss-Valdez. Okay, so you need stronger statement on localization, and it will be actually very important for this type of result. In particular, these states here and here are responsible for the plateau of the celebrated integrated quantum Hall effect. I mean, if you don't have these localized states, then you don't see the plateau. In particular, these gaps don't help at all to see plateaus in the quantum Hall effect. You need localized states, just because there is no Fermi energy here. You can always, in mathematical terms, move an energy inside the gap, but physically, either the last field level is here or it is here, but there is nothing here. So to see the plateau in the quantum Hall effect, you need localized states. And Anderson, and an interesting point is that Anderson localization like this is not enough to prove the plateau. It is not a theorem. The theorem is that if you have a stronger signature of localization than you have the plateau, I do not have a proof that this is not sufficient, but I do think so. Okay, so strong localization. That would be, for instance, get informations on correlations of the wave functions at 2 points. So prove something like this. C, this is C omega, and then one constant that will depend on psi. I think this does not depend on omega. and this alpha is actually equals to, let's say, the exponent, we don't care about the exponent. We just need something that is summable. And so another way of writing this is to see that this is x minus 2 psi, the trace of psi, or let's say where p psi is a projection on psi. Okay. So the big difference between this type of thing and this type of thing is that you have a control on what happens when you change your eigenvalue. Okay.
So in brackets x and brackets. What do you mean? I just want to be sure.
Very well, no, it's conventional.
So you have one way to get strong correlations like this, exponential decay like this, and a control on the constant that is in front. One way this is actually a consequence of what I will write now. So in particular, dynamical localization, you solve the Schrödinger equation, and you ask that you will say that an energy belongs to a region of dynamical localization, okay, dl, if there exists an open interval J that contains E, such that wave packets with energy in J will not spread. So you take something that is initially localized near 0, you take a function, a smooth characteristic function of J. So this is electrons prepared in the following way. They are located near 0 at time 0 and with energies in J, and you evolve and you take moments, let's say P over 2. I will take the Hilbert-Schmidt norm, then square, supremum over T, expectation, and this is finite for all P. This turns out to be equivalent to the decay of the Fermi projection. For instance, if PE is the projection on energies below E, then you may ask that this kernel decay fast enough. Sorry, I have to put some extra things. To some power k minus. So it has to decay at least exponentially. Okay, what I mean, so I'm just describing properties of the region of localization. So in this region of localization, you have non-spreading of wave packets in this sense. You have actually sub-exponential decay and sometimes actually exponential decay, we cannot get psi equals to 1 in all situations. But at least you always have sub-exponential decay of the Fermi projection, okay? And this is actually equivalent to the set of energies, where you can perform a multiscale analysis. And this is equivalent to the set of energies where you can perform a fractional moment method. So when these methods applies, then they are all the same. Okay, they give the same set of energies where you get localization. So what I mean, so this is proved mathematically. Okay, that as soon as you can start a multiscale analysis, then you have the conclusion, and if you have the conclusion, then you can start the multiscale analysis of fractional moment methods. Okay, so all these are equivalent, and in this region of localization, you have plenty of properties that are equivalent. Okay.
So this statement is just about the equivalence of different ways of approaching.
Yes. You can say so. It's so I put quotation marks not because it is not proven, just because I wrote it in a soft way, but in a sloppy way. But it is a theorem, and the theorem says that as soon as you can perform the multiscale analysis, the region where you have such properties is exactly the region where you can do a multiscale analysis or fractional moment methods. Okay, exactly. This is actually a result of Abel and I don't remember the year. Maybe 2003 or 4, I don't remember. Okay. Okay. And a consequence of this, we can get a bit more. Consequence of this is that you have a statement on the delocalization region. So delocalization will be the opposite of the dynamical region, and one result in this same paper is that if you are not in this region of strong localization, then you have a minimal transport. So I just want to recall this. If E does not belong to the region of dynamical localization, and if let's say Wegener holds, then you have some spreading of the wave packet, and the spreading is the speed is like this. You take the same quantity, so expectation x p over 2 h omega f j of h chi naught. Okay, I will consider the same time averaging as Jonathan did yesterday. So this time averaging, and okay, then if you consider Fj, which is 1 near E, okay, this is actually flat, and you consider the average of the moments of the wave packet, then this grows faster than C times P over 2D. So here it is 4 actually. Well, 2D minus 6, and And here, lambda, we have d equals 2, right? So it's p over 4. Okay, so this is something that I will use, and okay, and so I will keep these pictures and I will proceed. In particular, you cannot have a slow transport, for instance. But, okay, this is now an old result. Okay. So maybe the main result of first paper with Abel Klein and Jeff Schenker is that in the Landau case, so Landau, okay, there exists for any n, there exists an energy En such that En minus Bn is smaller than some constant Kn log B over B, such that En does not belong to the region of dynamical localization. So in particular, you have transport. And so this combines several things. This combines results on localization result on localization on Landau, and these are results obtained by Wei-Ming Wang, Combi-Slope, and Abel and I, which basically tells you that you have localization up to a distance log B over B from the Landau levels, and properties of the whole conductance, and this theorem. Let me say the localization, delocalization theorem. Okay. So I can come back. Yeah.
About that theorem, is there a difference between question and need? Or is there a result about don't take expectation?
Here you need expectation. I am positive.
There is a difference. No,
Yeah.
Quench would not be.
No, I don't think so.
Okay.
I don't think so, because from this you have to extract something that is true in probability. No, it would not be. Well, then it would depend on the control on the constant here. If you can get some control on the constant in omega, this constant will depend on omega. And
no, the question is whether at all it will be at this stage, or whether for each thought, high probability it will not grow like that for a given moment. That was my question.
Is this
No,
dominated by
I don't know.
events?
Yeah, because it could be that this thing is just due to some unlikely environment.
So is it probabilistically robust? For many orbits.
I don't understand this statement. I'm asking, is it with high probability?
Yeah.
It is in expectation. I cannot go.
So there is no.
No. Okay, so what happens here if I blow up this region? You have B here. You have some localized states here. The size is of order log B over B. And this is for B large enough. Sorry, I forgot to recall this. And there is somewhere, there exists some energy for which you have this type of delocalization, of dynamical delocalization. And one funny thing is that although I did not wrote the details, but I think I can prove that if there is, for this model, if there is an energy of delocalization here, then the exact symmetric should be also an energy of delocalization. Okay, but this has to be checked. I did not wrote everything down, but then if this is true, it looks a bit weird because, no, it's not weird. If you have something like this, then you expect that actually all the interval in between is filled with delocalized states, but this I cannot prove it. So I don't know if you have two energies of delocalizations like this. Unfortunately, mathematically, we cannot say anything about what happens in between. While we don't expect localized states here. But I just
but can you exclude the possibility at this point?
Yes.
Of the band?
Yeah, there could be just one. They can be just one. Yes.
No, and isn't the standard argument that it is just the center of the band?
I agree, but I cannot prove it.
No.
Yeah.
I'm trying to ask what is known in some way, what you call as a conjecture, that it is just the one state in the center with infinite localization and?
I don't have any conjecture on this. I leave this to physicists, and I think that physicists do not agree on this.
They don't okay.
I think they don't. Yeah, and
just since
I think that
since you mentioned physicists,
yeah,
question. Do you see? Don't touch physicists. It doesn't go without punishment. If you look at your left domain of localized states and the right domain, do you know qualitative difference between these functions?
No.
Because
Mathematically, we don't. It may be.
In physics community, there is belief that there is topological difference, and if this is true, and these things are not are really different, then independently what is UB, whether it is large or small, this gap cannot disappear.
This gap cannot disappear.
Yeah.
You mean what? This?
It cannot collapse. It may be single point, but
yeah, it can be. Yeah.
No. But my point is that there is a difference. There are topological numbers corresponding to left domain and right domain, and they are different.
But this is related to the whole conductance, which is 0 on the left and 1 on the right. Is that what you mean?
Yes.
Yeah. Okay. But this is used in the proof.
Sorry?
This is used in the proof of this result.
Francois, one more question. This EN doesn't depend on realization, right?
Yeah.
For each realization you have some EN. What is the statement? Is it universal for all the realization, or it's individual?
I think it's individual. Jeff? I think that EN depends on the realization.
Is the infinite system?
Yeah,
Is the
it
infinite
does.
system?
Yeah.
No. The delocalized energies.
Right.
Yeah, but because what we have is that there exists EN. We don't know where it is, and for different configurations, it can be a different one.
That they are the same for the same.
In fact, we know that there's a single EN at which
for each
the
realization
It can be
thing
different.
is violated.
for each
No,
realization.
there's a single EN independent of realization for which the it has to be used. I'm about to say quenched, where the quenched thing is violated. But in fact, as Prof just pointed out, we don't have. I'm sorry, annealed. I'm getting these backwards. These words straight. Where the annealed thing is violated, we don't have a condition of quench either.
So the answer is that you cannot prove that it doesn't have
No, of course it does not.
No.
Because in the infinite system,
My
it
question
does
is what
not.
is
What can be proved?
what can be proved?
That's fine.
Different.
So we don't know. That was a different indication.
No, the energy itself will. We don't know the energy itself.
We don't.
We don't know. We just know that there exists one. Okay.
You don't know where
I mean, your theory can be true for any disorder, because if the disorder is too strong, then you might not have this jump in conductivities at the lambda level. This is very some result you mentioned.
This result is for lambda fixed, disorder fixed, and B large enough.
I'm afraid that we have now at least 3 groups of discussions. Older.
I'm firm chairman here.
By the way, how much time do I have?
You have 22
Well,
minutes.
speaker.
We can add this.
Okay.
You have 50 years.
So one thing that is interesting to see, for instance, is how to see that strong localization, and in particular this type of thing, implies the fact that the whole conductance is constant. So strong implies that the whole conductance is constant. So what I mean is that I put myself in a region of localization. Okay, so you have plenty of states and it is dense. Okay, and the whole conductance is defined like this. If you take an energy at an energy E, it will be expectation of the trace of PE, P a switch function, P a switch function in the other direction, like this, okay? Where lambda 1 of x1, x2 depends only actually on the first variable, and it is something like this. It is a switch function, okay? Switch function in first direction and switch function in the second direction. And PE, I remember you, it's a Fermi projection, so all the states below E. Then, if E is included in a region of dynamical localization, where you actually do have this type of estimate, then for any E prime in I, sigma H E is equals to sigma H E prime. So actually I forgot, here are minus 2 pi, I think. And so the point is that you can unfold, for instance, one thing to notice is that you can unfold these commutators, and for P almost every omega, what you have is that the whole conductance is equals to the trace of P lambda 1 P, P lambda 2 P, okay? And let me maybe. And if you consider just one state, then it is immediate to see that this thing will be 0. So first, sigma h of E prime minus sigma h of E is actually equals to minus 2 pi trace of P E. Let me put a tilde. P tilde is equals to P E prime. So the spectral projection between these two energies, E prime, okay? Lambda 1 P, P lambda 2 P. You can actually prove this, And it's interesting to notice that if P tilde is just a single state, so projection on psi, for instance, then this trace, okay. Let me define it as theta tilde. Theta p psi is equals to 0, because you can unfold the commutator and it is 0, okay? So what okay, so in particular, the only way for the whole conductance to be non-zero is to have an infinite number of states, of course, but everybody knows. So more interesting is if you are in a region of localized states, then you have an infinite number of localized states. This P is an infinite superposition of states like this, and it is not clear whether this is still 0 or not. If you have an infinite number of states, then it is exactly this condition here that makes the job. So with this strong localization, actually the fact that the summation of all these constants alpha, omega over n equals to 0 to infinity is finite. It is actually equal to the trace of x minus 2 p tilde x minus 2, and it is finite. This tells you that you can actually somehow inverse the summation here and the computation of theta, or of the whole of the conductance, and this gives you that theta of p tilde is equals to 0. So again, it is the fact, it is because you know that that you have a constant like this with a good control, and the fact that you can sum up over all the eigenfunctions and get something finite, it allows you to invert the computation of the trace and the summation over an infinite number of states in p tilde. Okay, p tilde is the sum of many eigenstates, and you and so you get p tilde equals to 0. One thing that I would like to notice is that this does not use ergodicity. And for instance, if you go to Delaunay sets as an underlying subset for the location of your random impurities, then you can actually still use all this machinery, and you get control and properties of the whole conductance. Okay. So now, how does yeah, I can.
One question.
How do you do with the proof? And that will make a transition with this type of problem. What you do now with the proof is, you know that the whole conductance is 0 here, and that it is 1 here. So this is still lambda equals to 0, and this is lambda strictly positive. So the whole conductance is 0 here. You actually can prove with, it's quite easily that if you remain in gaps, then you can increase in the disorder and the whole conductance does not move. So here you still have 0 for the conductance, and here since you still have a gap is not closed, then you still have 1, and then you can move for a given lambda, you can move in the energy direction, okay? And as long as you stay either in a gap or in a region of localization, then you can apply all this, and you conclude that sigma is still 0 here, and sigma is still 1 here. Okay? And again, the fact here you don't need ergodicity, but you used in a crucial way the fact that you still have a gap that allows you to go up in the spectrum. Okay? And since you have 0 here and 1 here, you can conclude that somewhere in between you have to escape from the region of localization. Otherwise, because of the previous statement, the whole conductance should be constant. Okay, and this is your proof. So now the question is what happens when you don't have gaps anymore to help you. So in particular in the Gaussian case, the result is for lambda small, and it says that let's say that the distribution of the probability, the density of the probability distribution decays like minus omega naught to some power alpha. Okay, so alpha equals 2 is the Gaussian case. Then there exists En, I will put an omega, that does not belong to the region of delocalization, of dynamical localization. So you have an energy of delocalization such that En, so this energy is close to the Landau level up to a factor C that depends on n lambda log lambda to the power 1 over alpha. Okay, so this is the result. And to do this, of course, then you cannot use gaps like here. You immediately jump from a situation where you know what the whole conductance is to another one where you jump another one where you have localized states and okay, a priori you don't know. So to prove this, you need much more information on the whole conductance. In particular, here you need ergodicity, because with ergodicity you will be able to prove that the functions that sends E to the whole conductance at Fermi projection E is integer valued. And so, if you know in addition that that sigma h is continuous, then you will conclude that in the regions where this is true, okay, the whole is actually a constant in so actually this is in the region of localization. We can prove that this is true. And if you add continuity of the whole conductance, this will imply that the whole conductance is constant. Yeah, it's over? Yeah? More or less. Okay, so just let me give a few references for this, and I will stop. So strong properties on the whole conductance were derived by Avron, Simon, and Zeiler. And here, the Fermi energy has to be in a gap. So for this case, it is not useful, but it is in L2 of RD, of R2. So it is a continuous result. And there are also results of Belisar, Van Nels, and Schuss-Valdez, and also Eisenman and Graf, where EF belongs to the region of localization, but it is for L2 of Z2. It is for the discrete model. So what we did in a paper that we recently posted, that we have recently posted with Jeff and Abel, is to go back to the strategy of these two papers and to adapt them to the continuous case and to the region of localization to prove that if you have a finiteness of some localization length, then the whole conductance is integer valued, and then you have to prove that as lambda goes to 0, both the density of states and the whole conductance are constant up to lambda equals to 0. And if you have this, you can apply the same strategy because you would know that here the whole conductance is 0 and that here it is 1, and then you can conclude. And that will be my conclusion. Thank you.
Thank you very much. You wanted to say something?
No.
Okay. Anybody else has any comment or suggestions?
I have a comment.
You want the mirror?
Yeah, exactly. So I would like to ask the speaker whether he knows in the physics literature what is the diffusion. Okay, so thank you for your question. I recently asked Merlin, and he said that instead of 1/4 here, it is people believe to have 1/2, so diffusive behavior, but so in physics, but okay.
The speaker doesn't know anything, but
no, and the
he's
speaker
able
doesn't
to
know anything.
refer you to other people.
You're not a speaker, you're a chairman.
Speaker is the chairman. Oh, in England, the speaker is the chairman, isn't it?
No.
Isn't it?
No.
In the parliament, it is.
No, in parliament he's not.
So I think that before we go into this linguistic dispute, this is coming, the workshop and the programs are both coming to the end at the same point. I think that on behalf of everybody present and absent, I would like to thank the organizers, present and absent, for their contribution, for the work, for the ingenuity, for the effort, for the good taste, and I wish the speakers and everybody else good speakers, good flight return home. Those of you who celebrate New Year and Christmas, Happy Christmas and Happy New Year. Those of you who celebrate Hanukkah or any combination of the three, Happy Hanukkah. And I hope we should meet next year in Newton Institute. And the conference, I think, is declared